Okay, so good afternoon or good morning, everyone, and thank you for being here. So this afternoon is actually our last seminar of 2023. And for this seminar, we have the pleasure of welcoming Professor Nicolas Coltice from the Department of Earth Sciences at the University of Côte d'Azur in France. And he will discuss a very interesting topic, which is the relationship between the Earth's tectonic evolution and actually the lithosphere-mantle dynamics. So, Nicolas, the floor is yours.
Thank you very much. Thank you very much for the invitation. It's a pleasure to give this talk. So I'll start with with this. If it ever starts, would be nice. Sorry, yes. So what you see here is a famous image. It's a hologram in a famous movie. I guess maybe some of you know Star Wars. So this is a hologram. So, and what is a hologram? To make a hologram, the fundamental principle is to capture on a photoplate the interference produced by the light reflected by an object and the light coming from the source that is not disturbed by the object. So we collect it on a photoplate, and this is the photoplate you get. And then you have to illuminate this photoplate, and you get back the 3D image of the object. And so this is the plate you have for the hologram. And each point of that plate, it contains almost the complete information on the image that forms this object. So if you cut the plate into pieces, you can still produce the 3D hologram at a lower, even if it's a lower resolution, you still have the image of the hologram. And if you cut the pieces again, you still have, you know, the image. The resolution can be lower, but you have all the information. And so the hologram is a relevant metaphor for certain complex systems, such as the one we are going to study today. So, and this was introduced by this philosopher here, Edgar Morin. The hologram principle means that not only the part is the part in the wall, but the wall is somehow inscribed in the part of a system. So rather than a part and whole antagonism, the metaphor addresses issues about the nature of the dialogue between the whole and the part. So it's not individual against society. It's what is the dialogue between both cells and living being. And for us, it's the dialogue between the rock and the planet as a whole. Yeah, so this is going to be my talk today. Tectonics is a hologram. So I will use this concept to talk about the relationship between tectonics and mantle convection. Sorry for the sound. So the whole is within each part. So for instance, in the genetic code, there is a program for the cell, for the life form. So and from this program, it is possible to develop a cell of the liver, of the retina, etc. And so everything is in there. So this is what we can call the program. So in the Earth system, what is the program? The programs is within rocks that are made of atoms, which form minerals that you can see here, for instance. And these rocks, these minerals, they will form a rock, and the rock together, they will produce the mountains, the basins, the volcanoes, all what we have that is in so much motion at the surface. I just let this little video go just for the image to go from the smaller part to make the mineral, and then the mineral makes a rock, and all the rocks together, they will make the solid silicate part of the planet, which is the mantle and the crust. Yeah. All right. So we're going to leave climate and life. It's too big for today. So I will reduce the problem of the dynamics of the mantle and lithosphere system, and I will take a modeling approach. This is why I show here a sort of DNA, which is a digital one. So what would be a program with a simplification that would give rise to a whole dynamic system, which is with interactions everywhere. The program is well known to geologists who have their noses on the rocks, but it began to be modeled only 20 years ago at the scale of the mantle. So the work that is this is work that has been proposed in the 90s, following on, and what's really important is that these rocks, they have fundamental properties that will generate convection in the mantle and generate tectonics. So it's just been 10 years that this has been to a level that we can really study both together, and these are the paper presented here. I'm going to give some details so that you can understand this program. So the first ingredient of the program is the heat that is produced within the rock. So radioactive elements are there and can give energy. So the energy in the system, the heating of the system, sustained heating, sustained energy in the system is the first ingredient of the program. So what connects the rocks in the system, here they are physical, are modeled with physical laws. They are local, so they are the scale of the rocks. And these are mass, momentum, chemical species, and heat that must be conserved. And so these laws combined with the model, with the sort of program in the rock, properties of the rock. These are these laws that would produce the self-organization. So when you have these laws here, so you have the pressure gradients, like the forces, the buoyancy forces, the viscous traces. From just knowing these equations, you don't know what are the shape of tectonics or the shape of the planet that is going to come. So nothing a priori makes it possible to know beforehand. So there is a self-organization that will arise that will give the shape, the form of the system. And so the first very important property that second property that we need, so there was heating within the system. And then the second one is when we want to express this viscous traces. So here I show here a glacier. What you see is ice that is flowing. And so this is a solid that is sort of viscously flowing. And this is in a way sort of analog of the rocks. The rocks at the scale of the geological time scales, they are flowing like this ice is flowing, but much more slowly. And so this is the second ingredient, which is what we call the rheology. Here the model is a viscous model. And this is really a very simplification of the program. So on the scale of millions of years, the viscosity of the rocks. And the viscosity of rocks is extremely dependent on the temperature. A cold rock, the surface is almost rigid. The viscosity has almost no meaning in reality, maybe not what we want to look for. But as the rock it gets heated and it gets hot inside the planet, then it's flowing and flowing more easily. So viscosity is extremely dependent on the temperature. So when you put the internal heating, radioactive heating, and this type of viscosity into the equations, and you solve these equations with computers, then you produce this type of convective motion. So what you see here is the temperature in colors inside. So what you see that the temperature is quite homogeneous. And you have big plumes that start from the base of the mantle, the core mantle boundary, and they rise up to the surface. You have here an isotherm that is colored as in white, so that you can see the sort of the base of the lithosphere here, and you can see that there are little drops that are sinking into the mantle. So this model that Maëlys Arnoux has computed shows a planet for which there is not really tectonics at the surface. There is some topography caused by the plumes, but there is just one plate. It's a one-plate planet. The lid at the surface is quite homogeneous and nothing really happens. So this is not enough for now. The program is not enough to generate tectonics. It's enough to generate convection, but not enough to generate the tectonics we want to see for the Earth. All right, so cold rocks, they have another quality that they are deforming more easily when a stress threshold is reached. So I use this image of the tree because maybe you know, if you have seen rheological diagram, they look like a tree. So on the left, it's a real tree, so it's rocks, and on the right, it's what the geodynamicists they use. It's not a real tree, it's a plastic tree. And so it's what we use is pseudo plasticity. So it looks like the rheology of a rock, but it's not the rheology of a rock. What it means here is that there is a threshold, a stress threshold, and when this stress threshold is reached, the viscosity of the rock drops, and there is localization of the deformation that arise. So this is the localizing behavior of the deformation of rocks when they are cold. And so when we have this pseudo-plasticity into the model that we put, then we have a sort of expression like this. This is a simple model. I mean, there are other models. I think you had a seminar with Dave Berkovici, who proposed you details of the physics that can be behind that and can show a more complete rheological behavior. But this is what you have here. Mu is the viscosity on the left. Sigma y is the stress threshold sort of limit that the rock can handle, the yield stress. And what you have below is the second invariant of the strain rate. So it's the velocity of deformation. Some people can talk about it like that. And so if when you reach the stress limit, sigma y, if epsilon dot epsilon increases, then the viscosity drops. So this is the equation you have to localize the deformation. This is one way to do it. There are other ways. And so when we put this ingredient, then we obtain this model that you have here. So you see the colors of the inside. You may see blue downwellings, blue slabs sinking into the inner mantle, and you still have the plumes that arise from the deep mantle. And at the surface, you can see the topography at the surface, and you see here mid-ocean ridges. You see trenches for subduction. And so here you have the self-organization that corresponds to what we have, what we can see on Earth. So just by putting this important information, heat from radioactivity, and a description of the viscosity of rocks based on temperature dependence and a stress limit. By comparison, here there is a view of the tectonic kinematics of a system or convective system in which the viscosity would be constant. So it's not dependent on temperature, not dependent on stress. So the image you see here, so when it's red, these are the places where there is divergence, and when it's blue, it's the places where there is convergence. And in this type of model, the surface, the kinematics of the surface is not plate. Doesn't look like plates because there is deformation everywhere. A plate will have a similar angular velocity within all the plates, which is something that doesn't happen here. Okay, so here, for instance, there are plumes that touch the surface where there is divergence, and when at the crossing of the divergence patterns, you have the downwelling. You have downwelling plumes. So this has nothing to do. I mean, this is not what the Earth is. All right. So now I just want to show how some qualities that express themselves. tectonics is expressed from the rheology and the energy law, and one piece of rock, in a way, tells us nothing about the tectonics. Tectonics is an emergent property of the complex system. So it has to be all the interactions between rocks that produce what we see, the self-organization. And so this is a witness of the self-organization of the rocks between themselves. And in this case, it is clear that the whole is more than the sum of the parts. We see some form that we could not see just by looking at one single rock. So here, for instance, you have the flight of a group of birds that illustrates that point. And here you have a model. Can it work? So what you see here is one of these properties, seafloor spreading. So here you see that is an emerging property. On the left, you have an hemisphere on which you see the depth of, in a way, the depth of the lithosphere. So where it's red, you have mid-ocean ridges. Where it's blue, what you have are trenches that are when you can see subduction of these trenches in the upper mantle on the right side. It also goes into the lower mantle, but I don't show it because it's going to be tricky to see. And you can see the interaction with the plumes as well. So this is one emergent property that you have. You know, the plates, they organize themselves, plate boundaries emerge on their own. Subduction initiates, and a new ridge system initiates as well. Another property that you have here is continental drift. So what you see in the shaded area here and here are continents that are in motion at the surface of the model, dragged by subduction mostly, a little bit by the mantle. And so what you have, continental drift is an emergent property of this mantle lithosphere system. Just putting these energy properties and rheology properties. So we had aggregation of a supercontinent, but there is also the development of new subduction zones that will give rise to you know, the split of this continent. So you can see the supercontinent that it starts here to disrupt and dislocate. So this is something that that also appears in just when you put this property, this parameterization. And so you have supercontinental cycles in this type of model. So here it's taken from a paper by Tobias Rolf in 2014. It's with the type of model I showed before, in the same kind of physics. You have here only two continents, and we were looking at how these continents, they would aggregate and disperse. And so what you have here, if I can find back my, oh, I don't see it. Well, what you have on the x-axis is the time. You start from 0 and you go for billions of years, so it's in million years. And what you have in color is when you have supercontinents, when it's gray. When it's white, continents are dispersed. The difference between A, B, C, and D is the yield stress value of the system. So when you are on top, the yield stress is low. When you are at the bottom here, the D is when the yield stress is high. So what happens here? When the yield stress is low, the stresses that in the convective system produce a lot of plate boundaries. It's easy to yield the rocks. So you have lots of plate boundaries. And so it's very difficult for continents to aggregate, because once they start to aggregate, there is a new plate boundary that is taking the continent somewhere else. I mean, there are too many boundaries between two continents. When you are on the D, at the bottom, there are not so many plate boundaries because it's very difficult to yield the rocks. And then if you have just one plate boundary, continents will aggregate, for instance, one subduction, for instance, one subducting system, supercontinents will aggregate, and then it's going to be very difficult to sort of break them apart, and so they will stick together for a long time. So there will be more time of aggregation than splitting in this case. And there is an intermediate intermediate area of yield stresses that you can see in B and C, in which there is sort of a cyclicity of supercontinent cycles with times where continents are split are kind of similar order of magnitude of as the times of the continents are together. So depending on that yield stress, you can change the supercontinental cycle behavior. With computer topology and computer vision methods, you can automatically determine where the plate tectonics can be on this type of models. On the left, the color represents the viscosity field in one model. And in blue and green, there are some topological very special points, Morse-Mail complex points, and in that helps to identify the plate. And so on the right side, you can see the automatically generated plate layout from the continuous model that we make. So we can compare then the plate tectonic, the organization of plates in the models to the Earth. And this was the work, the PhD work of Alexandre Janin that you see here. And so we can look at these distributions. And what you have here is this plate distribution. I'm going to talk about that later, but what you can see here is the two distributions that are the lifetime of plates. The lifetime of plates in the model and in the plate reconstruction models. And so it's quite interesting because what you can see is that the plate lifetime is quite small. On average, I think it's 30 million years or something like that. And the sort of power law that we get for both observations is typical of a sort of planned obsolescence of the plate. So in a way, a plate that lives longer will have a tendency to live even longer. So it's why I put this movie on the right. There is sort of planned obsolescence of the plate, given that the plate properties. It will die sooner. I mean, at a given time.
Nicolas, excuse me.
Yeah.
This is Alec. Which plate you are talking about? The continental plates or oceanic plates?
So here they are all together here, but it's mostly the oceanic plates. The continental plates in the models, they are stronger, and so they will live usually longer. It's going to be more difficult to change them.
Mm-hmm.
But they are part of this system, of this sort of planned obsolescence thing. Well, there is lots of physics to do to understand what's behind this type of distribution. But we can make this type of distribution from the models, and we can look at the distribution of the area of plates that you can see here. So you can see a snapshot of the model where you have the plate layout with the deformed areas. So here it's about, I think, 10 to 20% of the area of the model, which is quite similar to what you have on Earth. On the right, you can see in red the present-day Earth plate size distribution, and the curves that you have are in blue are those of the model. So there is a relationship between the plate area, the plate area, and the number of plates that you have in the model. So this distribution, we have ways to understand them. They are sort of power laws. And what we can see is that when we increase the yield stress, so this was the work of Claire Mallard, when we increase the yield stress in the models, you go here from the left side to the right side. So you have what you see here at the surface of these models is the viscosity of the model. So when it is green, the plates are strong. You are within plates. When you see red, it's plate boundaries. And what you see is that when you go from the left to right, plates are bigger and bigger. And so you are changing the distribution from left to right. And so the interpretation that we could make going beyond just the images is that fragmentation in these models, fragmentation of the plates, mainly occurs near subduction zones. And so all the distribution of the smaller plates is made a lot by what is close to subduction zones. And it's quite similar on Earth, with the exception of microplates around ridges. So small plates are found near subduction zones. And so in a way, the large plates here, they speak of the arrangement of subduction, so the sort of dynamics of the structures inside the mantle. And the small plates, they talk about deformation about subduction zone. And so there is a self-organization between convective motion, where subductions can happen, and how these subductions they fragment the plates around. So again, this is a self-organization process, and this is something that emerges from the collective behavior of the rocks. Yeah, in these models, the way the mantle flows is also an emergent property. I'm not sure I'm going to talk too much about it, but just to show here that there are different ways that the plates can be in motion. So what you see here, maybe it's not easy to see. You have the surface of the model. You barely see the topography on top, and you have a cut inside the model with the pressure inside the pressure related dynamic pressure of the flow. What you have in white is a contour just to show a sort of a slab here. So on the left side, you can maybe see a trench with a slab going down. And on the right, you have a continent. And between the continent and the trench, you have a back arc system. And what you can see is on the left side, the velocities at the surface, they are not in the same direction as the velocities inside in the interior. And so what it means is that the surface is a sort of surface is tracing the interior in a way, and you have a flow which is the velocities in the plates. They are not dictated by the mantle, by what is in the interior, but by the pressure gradients that are within this within the lithosphere. So you can see a very low pressure at the surface of the slab, which is attracting the plates. On the right side, what you can see is that you have higher velocities below the continent, below the continental plate. And when this is the case, it means that the motion within the mantle is sort of tracting the continents. And you can see there is a pressure high there, and again the pressure low close to the slab. So these pressure gradients, they are, whether they are in the lithosphere or below, they are controlling the motion, lateral motion close to the surface. So I have just shown how some qualities that are not in isolated matter in one rock, that you cannot see in one rock, they express when you put all rocks together, the collective, and the tectonics is then an expression of the rheology and the energy law when you put all these things together. And so just one rock doesn't tell us about tectonics. We need all the whole system. It's a self-organized system. So in this case, what I showed is that the whole is more than the sum of the parts. The flight of the bird was illustrating that.
Nicolas,
yes?
Excuse me, you showed the black slide.
Yes.
This one, it was your intention?
Yeah, my intention.
Okay, sorry, I decided maybe we don't. Okay, thank you.
Yeah, no, just to transit to the new one. So here, what you see here, an emergent property testifies that the whole is more than the sum of the parts, as I said. But another interesting thing in complex system is that the whole is also less than the sum of the parts. The organization of the whole can inhibit or prohibit some of the qualities specific to the parts. Qualities that cannot be expressed due to systemic constraints, for instance. So I take here an example of a basketball team. So you had here 3 of the best players of the world together, and they were not able to express themselves together to make the team win. So just to say also that maybe you do things in your apartment or where you live, or in your bedroom that you will not do when you are in society. So this is the kind of idea that when you look at a rock, there are lots of things that could be expressed, but the collective behavior also inhibits some of this behavior. Okay. For instance, here I just made a really rough picture. So it would be some sort of a model that we could design. We could design a model of a dynamic model where we have on the left, upper left, a sort of continental plate. And we would put 3 subduction zones very close to each other. And we can look at how these things can evolve. But the question is this worth looking? Because maybe when we take the global Earth, the self-organization will inhibit the existence of 3 close subductions together. Maybe, I don't know. But it's just to say that we can design, when we reduce the system to just a part of it, we can make some experiments, we can test some behaviors, but that cannot be expressed when we look at the bigger picture. So this is, I think, this is an important thing to know. It can also be illustrated, I think, in the same way in the global model. So here is the fragmentation of a plate when a plume is near the ridge. So these are both convection models. So what you see in color is the relative temperature to the mean. So it's more a little bit like a tomographic model in a way. So you see what is hotter than the mean, and blue is colder than the mean. What you see in purple here, this is the model continent. And you see in red the ridges, and in blue trenches. And they are I highlighted here the plumes that reach the surface. And so you see on the left side, you see a ridge, and there is a plume close to the ridge. 22 million years after, there is the plate, you have fragmentation of the plate, which seems driven by the plume. And so here I show you a case that is very similar to the first one. So you have a situation that is quite similar. An equally powerful plume. The distance between the ridge and the trench is quite similar. I mean, there are a lot of things that are similar. But in this situation, there is no fragmentation of the plates. So there is something here that inhibits the fragmentation of the plates, which was not in the model before. So this is also the type of behavior that we can look for. There is very rarely one cause to a consequence that we can identify easily. Again, this was a short, just a short message to say that yes, the whole is more than the sum of the parts, but there is also this inhibition of possibilities when we put things together, that the trajectories of convection of the Earth system is also constrained by all this collective interaction. And so not everything is possible when you say we can do everything in a model. No, it's not. When you take a model large enough, there is nothing is. It's not that everything is possible to model. You have some collective constraints. So I wanted to finish with a couple of properties of this type of system. And here I wanted to talk a little bit about the butterfly effect that was introduced by Lawrence to express the properties of the chaotic system. So mantle convection is a chaotic system. And the system of equation can be shown. I mean, working on the system of equation, you can show that, and you realize that also when you make the experiments and the calculation. And so it means that when you have small modifications of the initial conditions at a given moment, it generates a completely new dynamic trajectory. So which will move away from what was sort of planned without the modification. So this effect of sensitivity to initial conditions is very important in the complex system. And I show you here an illustration that was the work of Lea Bello. And so here what you see is 500 million years of evolution of a convective system with a plate-like behavior. So there is a very tiny change, tiny noise in the temperature field. And so tiny difference between the first column and the second column. And so you see, as time goes on, you have differences that start to express. And so, for instance, now the continents, they are close to each other, but the oceanic plates, they start to differ. The plate boundaries are not similar. The subduction zones are not exactly at the same place. So these slides, and at some point they can be almost bifurcation when a new big subduction starts in one model and not in the other model. The difference can go very quickly. So there are effects like that in complex system. When a slight change, a slight modification, a slight interplay over time will make a sort of divergence or bifurcation. It can be both of the planetary trajectory. And so, yeah, it's quite interesting to go deeper into that quote of Lawrence. So if a single flap of a butterfly's wings can be instrumental in generating a tornado, so also can all the previous and subsequent flaps of its wings, as can the flaps of millions of butterflies, not to mention the activities of innumerable more powerful creatures, including our own species. And if the flap of a butterfly's wings can be instrumental in generating a tornado, it can equally well be instrumental in preventing a tornado. So why do I talk to you about this butterfly effect and I give you this quote? It's just to say that in a self-organizing system, it's very difficult to say there is a rift, I don't know, in Asia somewhere, because there was a plume there or a subduction started there or there. Because this is not really the true cause of the system, because there are so many possibilities and so many inhibitions also that can exist in a complex system that in fact the causality cannot be the quest. If we say if we are looking for giving a cause to a rift, a cause to an initiation of subduction or something like that, the cause is difficult to find. However, what we can try to address is to see what is the parameters that we use in the model that can allow this type of organization, or these properties of the plates, or these properties of the initiation of rift and stuff like that. Is what I can propose here. So yeah. Okay, so this was for the sort of also this is about the inhibition of certain behaviors. So I come to the conclusion of my talk here. So conclusion was that the tectonics is an emerging property of the mantle lithosphere complex system. The program here is about rheology and heat sources. The whole is greater than the part, so there is emergence of tectonics, of a certain type of tectonics, depending on the properties that we set first. And we cannot look at a rock and know beforehand what is going to emerge. We have to make the experience. We have to go through the whole process before we see really what happens. The whole is smaller than the part. So when we say that, it means that not anything can be produced by the system of the equations. There is only a part of that can be expressed. Even some properties that we could see at a shorter, that we could imagine or produce on a regional scale cannot be expressed at global scale because of the collective behavior. And then the causality between two symptoms of systems, for instance, initiation of a rift and a plume, it can be an inappropriate question. So yeah. So one question is that if we have a program, if we have a parameterization that is sufficient, is it possible then to use it to reconstruct the tectonics and convection together back back in time and use a different reconstruction. So this is for the future. So thank you.
Well, thank you very much. It was interesting to see the Earth as a complex system with everything. And we heard a lot about plate boundaries, which was our topic of this year. So great talk. Thank you very much, Nicolas.
Okay.
Now the floor is open for questions. So either you put it in the chat and I read it for you, or you can raise your hands and I'll give you the floor. Yeah, Alik.
Yeah, well, thank you very much. Excellent talk, interesting. I mean, it's from different views and so on. Especially, I appreciate over the issues related to the holistic approach to the whole Earth, but not with the too much details. But nevertheless, the details is also always important. I have 2 points. You mentioned that it's with parameters like viscosity, you can manage the aggregation of some small plates into supercontinents. You didn't use this word, but it looks like that. And then it's splitting these supercontinents in some time apart and so on.
Yes.
That is well. However, I remember it was a time ago when Michael Gurnis, he really showed that these plates aggregates and stay for a while until this temperature will change dramatically beneath the supercontinent and will start to split them apart. And he showed in the 2D case, it's some paper in 17th in Nature published, and later the Valery Trubitsyn, he is a Russian scientist, he showed on the sphere, they say how continents moves, aggregates, and apart. The major point was exactly what Michael Gurnis told about this aggregation of continents which are moving toward the subduction zone in general. And then the subduction zone changed because of the insulation of the continents, and they instead of subduction zone occurs the upwelling, and upwelling start to separate the continent apart. This is one of the point how in the model did you use in the model, or did you observe in the model, which is a purely, let's say, quasi-plastic, and such kind of the behavior?
Yes.
This is a first question. If you wish, I can give a second or separately.
I take some notes. Go ahead.
Yeah, it's because it's a discussion point. Yeah, and another issue also is quite interesting about you mentioned chaotic system. Well, actually, in which sense? In sense of the increasing Rayleigh numbers. I don't hear after the recording by Dave Ewan, our good colleague, unfortunately passed away, and so on. Probably you heard about it. And he made some records like Rayleigh number 10 to the 12, 10 to the 30, and so on. Nevertheless, we don't have such kind of the Rayleigh numbers to generate real chaotic mantle convection. From other side, if you will go to the Prandtl number, it's if you look at the mechanics, also fluid mechanics, it's when we have a really very high Reynolds number with a very small, let's say, Prandtl number, then we can get this truly chaotic, purely chaotic system, because it is a weak nonlinearity in the mantle convection actually equations. And how much the really this butterfly effect would influence the system because of the anyway very high viscosity.
All right. So I start with the insulation and breakup of the supercontinent. So here, looking at the temperature between the supercontinents, sorry. Here, looking at the insulation between below the supercontinent, is more looking at the symptoms of the system. So is it the insulation of below the continents that split the continents? I'm not sure. What I'm sure here is that when I change the yield stress of the system, if I decrease the yield stress of the system, it's easier for supercontinents to break apart. And so when they break apart, sometimes it's hotter below the supercontinents. Sometimes it's not hotter. So there are conditions to in 3D with this type of rheology to have a hot insulation below the supercontinent. I mean, it happens most of the cases, but I think Adrian Lenardich has talked about that before. But when if you add a sort of ring of subduction around the supercontinent, then you can understand why there is insulation below the supercontinent. But this rarely happens in the model, let's say. But in the simulation I showed you, there is a heating below the supercontinent. But it's not that breaks the supercontinent apart. Yeah, it's really and I'm not sure if it's fair to talk about it, to say that. But if we look at the stresses, the forces, they are more in the lithosphere. So this is why I'd say this is more what happens at the trench with that. I mean, subductions that are breaking the supercontinents apart. So on your question about the chaotic system, here we can show just using the equations that when we are at Rayleigh number 10 to the 6, I think, we get the chaotic behavior. I mean, we can look at the equations, but also make the calculations. And maybe it's not turbulent, but it's chaotic. And the time scale of when there is a perturbation, this perturbation is growing by a factor of 2 in 100 million years in this kind of model. So it's more a long term. But when you talk about models with pseudoplasticity, you can have some sort of bifurcation. So if you perturb it strong enough, then the model can potentially shut down plate tectonics, or this kind of big. You can have this big change that can be much faster. But a small perturbation will take quite some time to change the whole system.
Is a code by Tekle, by Paul, you use in spherical model?
The code of yes, of Paul Tekle, like YY.
Okay. Joao Duarte has a question. Joao, please.
Yes, I can ask. Can you hear me?
Yes.
Yes.
Hello.
Hi, Nicolas. Thank you very much. Great talk. I love your work. It's something that I have on my mind, from reading your, but I think I never had the chance to ask you directly. So I think these models are great because you start to see a lot of feedbacks and a lot of emergent phenomena. And this really puts in gives us a different perspective, from the classical, like mantle convection drive continental drift, and then in a way the plates are part of mantle convection. Do you think it's still useful to say? This is one question. I think I have two. If it's still, we can say that plate tectonics is part of mantle convection. That's one of my questions. And how can we try to, if it makes sense to ask the question, what is driving plate tectonics? So in the sense, it's the plates driving themselves, or the plates generate mantle convection, then the mantle convection feeds back on the plate movement. Or if it's more useful to think about energy. What is the energy in the system? What is driving? What are the sources of energy in the system? And if yes, in your models, where is most of the energy? Is the negative buoyancy of the plates? There's like a strong upwelling that could drive movement. So yeah, I would just like to hear what you think about it.
All right. So I guess I will need more time to think about it and maybe talk to you and other people to make some maybe a better, clearer statements. Is tectonics part of mantle convection? I don't know. It's yeah, I'd say it's an emergent property. It's some people say it's an expression of mantle convection. It's one form of the solution of this problem. What is driving plate tectonics? Is it more useful to look at where the energy is? I think where I follow you here is that, especially when we solve those type of equations, we solve local equations in a big thing. But we look at things that are local, so we can look at where things are, and energy buoyancy is certainly yes what we want to look at. So I think I would follow you there. Where are the pressure gradients? Where are the buoyancy forces? Yes, sort of. Then also we can get with this type of models, we can go into topological discussions as well. So where are the things? What are their forms? Where are they located? How do they change in times? So I think yes, it's quite appropriate to have a sort of regional or even local view of this big system, and don't just look at them as a just look at one plate is reduced. I mean, it's very good for plate tectonics to have just one pole, one Euler pole, and one angular velocity, and we explain everything at the size scale of the plate. But when we look at the dynamics, then this can be too much of a reduction of the system, I think. I don't know if I've answered your
No,
question.
yes, I think the problem with these models is that you have like huge outputs, and it becomes a little bit difficult to make the queries. And maybe I think you showed the point. You said the important thing is that maybe these things are constantly changing over time.
Yes.
So you have to be careful, if it's bottom up or top down. Maybe maybe it's both, and it's oscillating, over time, right? There's some periods where the downwellings are very important, but then this will feed back, and then you'll have a period after that the upwellings are very important.
Yes, yes, oh, that's right. And then it's very often too quick to make a causality statement.
Yeah.
Because
Yeah.
as
Okay.
I said before, for the insulation of supercontinents, you have cases that can look very similar, and where the symptoms are a little bit different. And I think this is what we have also in the geology. It's very difficult to say that all the mountains, they form the same, or when you look at the rocks, it's always very singular, and finding what is the cause of what we see is very difficult. This is so multiple that maybe getting at the systemic, having a systemic view, and looking at what is the program that allows this kind of expression, and also this kind of the diversity of expression is maybe more interesting than just proposing a way to form mountains.
Yeah, no, I fully agree. Yeah, no, I fully agree. Thank you.
Thank you.
Okay. Any other question? No, I think we're all fine. Like everyone asked a question.
Actually, it's one more question, because it was quite
good.
interesting. Nicolas, you also showed there's some map, I think in 3D, it was related to the pressure. And actually, I didn't understand what the pressure within the body, I mean, within the lithosphere change. Here, exactly. And if you will see, I mean, this is a blue, like, the horizontal slab. What is that?
What we have on the right side, you mean upper right?
On the left side, on the left side.
On the left side here. Oh, you mean here? Oh, no, here.
I don't see your.
So
I mean,
here.
where it is just to the left side, and yeah, At some low level, something like I don't know, there is 1/3 from the scaling up.
Okay, so this
There
is
is
the
a blue, because blue compared to here, it is just atmospheric pressure. I don't understand why beneath the Earth it's atmospheric pressure exists.
So this is the dynamic pressure. So this is the pressure relative to the lithostatic pressure.
I see. Okay. Okay.
So
That's
yeah, so
dynamic
this
pressure.
what you show here are the pressure differences within the system caused by expressed by the convection.
I see. Because you mentioned that it's specifically in the blue zone, the velocity is higher, but here velocity looks like a 0. That's why I suppressed a little bit. It's okay.
So here, for instance, you have a pressure high, and you go towards the pressure low. Right here.
No, that's fine. I am
Yes.
talking about this something which is just beneath blue one.
You mean
Very,
this one?
very blue.
This one, you mean, for instance?
No, that's up, as I understand. I am talking about down.
Here.
Yes, exactly. Exactly.
All right. So
Yes.
I guess this is between parts of the slabs. And so yeah, I cannot.
Because it's very close to 0 pressure, and that's why it's something surprising if it would be.
Yes, it's close to 0 dynamic pressure. I think it's probably a very stagnant point in the slab that is going down, in this piece that is going down. So it's probably somewhere where you have mostly, no horizontal I guess.
Which is interesting in a way, because there are many people who propose that there were some transfer from one side to another when the slab.
No.
Okay. So yeah. Anyway, Richard Katz has a question.
Hi, Nicola. I'm sorry I missed the first half of the talk because I had the idea that it started at 2:30. So it's not really right for me to ask a question because you may have answered it in the first half of your talk. But I'm interested, I mean, everyone's interested, I would say, in how subduction initiation takes place when you don't have a plate tectonic system. And it probably, I mean, I'm not sure that it's something that one answers with Paul Tackley's code, but I'm sure it's something that you've thought about. And so I wondered what you think about this sort of problem.
So you mean, I just want to make sure. So are you talking about subduction initiation like on Earth today, or do you look for when subduction initiates in a planet in which there is no subduction?
Yeah, more the latter, but
More
I
the
mean,
latter.
I don't want to be too narrow, whatever you want to talk about.
All right. So in those models, and from what I've learned with using this sort of orology, maybe I can use this as an example. Subduction initiates when there are lateral, strong gradients on density laterally. So it was not really too much of is the lithosphere dense enough? Because when it's very dense, usually it's very cold and it's very resistant, so it's very difficult to yield. But if I have a thin lithosphere and I have a plume coming there, then I have a very strong gradient, lateral gradient, and I can initiate subduction. So I think mostly in this type of system, initiating subduction I'm talking here on a sort of statistical equilibrium. You need to produce this sort of different. I think I made also a slide about this. Sorry. And then there is the question of inheritance, which is another story. But sorry, yeah. So when I have something like this, something hot and something cold, but it can be just something buoyant, chemically buoyant, or chemically, yeah.
Which way is gravity in this picture?
Gravity would go this way, right?
Okay.
And so when you have this contrast here, then it's really the lateral gradients that will generate initiate the subduction or the instabilities when you have to take into account the strength of the rock. So how can you generate that? This is the question. So it's a lot about making the lithosphere having differences in thickness.
Mhm.
And so this is the buoyancy part with a sort of homogeneous resistance. And then, of course, there are lots of questions about inheritance, making places that are weaker than somewhere else. But even if you have something weak, you need buoyancy to put the system in action. And so, for instance, when you think about the plume initiation of subduction, or when you think about people advocating for like impact craters, things like that, it's mostly what they are producing is that contrast here.
Mm.
They find a way to produce that contrast.
Okay.
Mm.
All right, that's interesting. Thank you.
Welcome.
Thank you. Any other question? No. So yeah, I will thank you again a lot, Nicolas, for your presentation,
Yes.
which was quite original compared to all the talks we have had before. So thank you very much. And yeah, I'm just going to stop the recording. So thank you very much. And thank you everyone for coming.
Thank you.